Hello, everybody. How are you doing? Okay, great. Well, I believe that I have everything that we need here. Let me adjust that just a bit. There we go. And if we are expeditious, we'll be able to get through this in pretty much 2 hours. So allow me to go ahead and share my screen with you. There we go. Okay. All right. So we're going to talk about the devices that make up prostheses. And what you see here in the picture are the feet of somebody who's had a rather long transmetatarsal amputation and very nice natural-looking prostheses. Okay, in fact, we're going to start with thinking about that level of amputation, especially the transmetatarsal amputation, which is fairly common. So the problem with a transmetatarsal amputation or something like that is, well, especially the transmetatarsal amputation, this is actually even true of a hallux amputation, which is pretty common too, is a loss of what's called a toe lever. And I'll describe that more on the next slide. But the consequences to that in gait is that the ankle rocker is shortened, the forefoot rocker is absent, and therefore the step length of on the opposite side is decreased because the patient is able to spend less time on the amputated side. I'll use this diagram on the next slide to show you how that works. So here we have the legs of a healthy walker with 2 normal feet. I think this was actually taken from an advert for shoes. But consider the left lower extremity. Here is the ground reaction force vector that's coming up from the toes, really. So the patient is about a 4-foot rocker, and the ground reaction force vector is going either in front or right on top of the sagittal plane axis of the knee. You see, so that is causing a external extension moment, right? And that external extension moment is allowing, let me just get a pointer ready. That external extension moment, yeah, that's not the pointer I wanted. There we go. Okay. There we go. That'll work. Okay, that external extension moment is rotating the tibia backwards and allowing enough time for the swing on the opposite side. So the patient would have an adequate step length. However, if a patient has had a transmetatarsal amputation, and what I did with this drawing was just erase the forefoot, so hopefully you can imagine that it's a patient who's had a transmetatarsal amputation, then that moves the ground reaction force vector from, in this case, the left foot, the foot that is in terminal stance, it moves it backwards. So now that ground reaction force vector is in back of the sagittal plane axis of the knee joint, and instead of causing an external extension moment, is causing an external flexion moment. This is actually something that we see pretty commonly in people who are using prostheses. This is a phenomenon called drop-off. And over the next week or two, we'll talk more about it. But the consequence of that is that their knee flexes early, and there is less chance for the opposite foot to clear enough ground. So you shorten the step, and because of the early knee flexion that the patient has. Okay, so what we can do with patients with this type of amputation is include a shank as part of the shoe or the prosthesis to lengthen the toe lever. And here, what you see is a prosthesis that somebody might have. Now, unfortunately, the expression shank has 3 meanings. One of them the meanings being the segment from the knee to the ankle. So that's something that we think of. One of them meaning this part of a shoe, or in this case, a prosthesis, something that just provides stiffness through the midfoot. And the third meaning is a homemade knife that is used in prison. That's not what we're thinking of, but we're thinking of one of these. Okay, so this shank that is going across the midfoot can lengthen that toe lever and give the person a more natural length by allowing them more of an increased external dorsiflexion moment, therefore an increased external knee extension moment, pushing the tibia backwards, so that they can get out over the swing leg and have an adequate step length. Support for the transverse arch is also something that is pretty important with patients with this type of amputation, because here in this diagram, what you see is actually an amputation that would have taken place at the Lisfranc joint. So remember, the Lisfranc joint is where the cuneiforms meet the metatarsals, and you see that there's a nice transverse arch, but there's nothing supported medially because you need the metatarsals to come down distally to support the transverse arch medially. So one of the things that can happen is that the transverse arch collapses and the foot goes into a severe hindfoot pronation pattern. Now, we talked a little bit about some of the midfoot amputations. So are the Lisfranc amputation and the Chopard amputation. So suspension is a challenge. And remember, we talked about suspension when we talked about the orthotics. Suspension is how you keep the device on the body. And if this, show you a little more closely. So if this is removed, or even a little bit more, this is removed, then there is just not very much to keep something shaped like a shoe on what is left of the foot. Okay, so here are the things that we're going to talk about today. Well, actually, we're not going to talk about the knee mechanism today. The knee mechanism is part of the transfemoral prosthesis. We'll talk about that next time. But the other things are all things that we're going to talk about over the course of this afternoon. Okay, we'll start thinking about the foot. The prosthetic foot is the link to the ground for an upright individual, and this is true whether we are using a prosthesis or whether we have 2 sound, healthy feet. And what it needs to do is provide shock absorption, and one of the ways it does is through controlled plantar flexion in the loading response. It's got to be a mobile adapter, and then a rigid lever to transmit force to the ground as we push off of that same foot. And there are some things that we do with our natural healthy feet that are very difficult for a prosthetic foot to do, such as medial lateral accommodation to force to surfaces, like you see in this picture here. And the reason I have this picture here is that the person's feet are really kind of conforming to that like slippery log is what it looks like it is, which is something that would, for a couple reasons, be very difficult for somebody using prosthesis, and also accommodation to the internal and external rotation forces and motions coming from the pelvis and the leg. So We talked about this several times, but it's a really important idea. So I'm going to show you, I'm going to stop my, well, first I'm going to show you a diagram, and then I'm going to show you with my body, because it's a really important idea. Okay, so remember, here is pronation, and again, this is a illustration of an individual with a very healthy foot, a very young person in pronation, and there she is in supination. Okay, and so I'm going to stop the share for just a second so I can show you what we're talking about here. Okay, and please, if you're not on there, go to the speaker view. So I'll be a little bit bigger so you can see what I'm doing. Okay, so I'm gonna, can you guys hear me okay? Give me a thumbs up if you can. Okay, good. Okay, so I'm gonna exaggerate this a little bit so you can see what's going on. As the foot goes to the ground, what happens in the transverse plane is that the pelvis goes forward. So if I go and step with my right foot, then my pelvis goes to the left. And the lower extremity, the right lower extremity is internally rotating, and that internal rotation has got to be accommodated by pronation of the hind foot, supination of the forefoot. So the arch gets lower, right? Which makes it a better shock absorber. And then I step past it, and again, I'm going to exaggerate this. Okay, and now my pelvis is rotating back to the right. So what happens with the lower extremity is external rotation. With that external rotation, in order to keep the foot planted right on the ground, you need to have supination of the hind foot and pronation of the forefoot. The arch gets higher, it's a better rigid lever with which to push off of. We've talked about this in a bunch of contexts over the course of the last few years. And even people like me and Justin, hi Justin, you look sleepy there, buddy. Okay, who's your buddy there?
This is Theodore.
Theodore, be sure to keep Daddy awake for this, okay? All right. Anyway, so even people with really flat feet, like Justin and me, this still works for us. You know, even though we don't have much arch, we still have a foot that's mobile enough to accommodate to those transverse plane forces coming from above. However, I'm going to go back to screen share. There we go. How do you do it with a prosthetic foot? First, we'll talk about why it's so important, because remember, why is it that 82% of prostheses, or excuse me, 82% of lower extremity amputations are done? Go ahead and chat me.
Diabetes.
So diabetes, yeah, no, you can yell it out too. Diabetes is an example. And what else? Chat or yell? Either one's good. Actually, I prefer the yelling. But Zoom makes people abnormally shy, I think. So diabetes is one, and diabetes is a part of a category of problems, well, I'll go ahead and tell you, called dysvascular problems, right? So if you're in this environment, you're talking about things like diabetes, peripheral vascular disease, hypertension. Those are all dysvascular problems. So 82%, you know, and it'll vary a little bit, but in the developed world, it's around 82% of people who have amputations, lower extremity amputations, have them for dysvascular reasons. So frequently, they have non-healing wounds. And what you really don't need with proclivity for non-healing wounds is friction, because that friction can cause scratches and abrasions on a residual limb. So we need something to absorb those rotational forces so they are not between the prosthesis itself and the residual limb, because that could cause scratches and abrasions, because those forces, those torques actually, are going to be happening someplace. Okay, sorry about the sound effects. That was Fred's idea. Anyway, so a type of prosthetic foot that was developed right after the Second World War is called the SACH foot. And SACH is for solid ankle compressible heel, SACH. So the way that this type of foot has, or the strategy that this type of foot has for absorbing the external plantar flexion moment is that the heel squashes with initial contact. One more thing, so here, if you look at this diagram, you can see that there's this softer foam that makes up the heel, and then there is something called a keel. And I've got another example here that I want to show you. So if you'll excuse me just a second. I know you're in there. There we are. Okay, good. Okay, so can you see this here? So this is a prosthetic foot that's had a big section taken off of the medial side. Here's the outside, and here's the inside. And what you see here is also, this is a little more advanced than the SACH foot, but this is also the keel. So the keel is what the endoskeletal structure of a prosthesis is called. And endoskeletal means like we are endoskeletal too, that our structural strength comes from our internal skeleton. So here is the endoskeletal structure. And with the SACH foot, the keel is usually made out of wood. Okay, so I'm going to just share this here. These are some advantages of the SACH foot, and you guys can all read as well as I can. But I do want to describe something that's kind of interesting. So for a couple generations, really from the end of the Second World War, when this was first developed and prescribed for lower extremity prostheses, through early in the aughts, so like 2000, in the early 2000s, it was assumed that if you were weaker, if you were older, that really you needed something like a SACH foot because it has no moving parts. And the moving parts are harder to control. But what some researchers found, let's see, do I have a description of this? Yeah, let's go back to this and I'll just describe what these researchers found. So in this study here, so this was done 5 years ago, or published 5 years ago, is that patients, these types of patients using prosthesis for dysvascular transtibial amputation, actually walked better. They were more stable. They had a lower energy requirement when they had what's called an articulated foot. So the articulated foot generally allows for plantar and dorsiflexion. Okay, and the reason why I want you to think about for a minute. So take a minute, please, and tell me why you think that these patients actually had better walking, that is faster walking, and lower energy cost of walking with a foot that could plantar and dorsiflex. I'll tell you, in fact, I'll give you a hint, the really important thing is the plantar flexion. Then the same patients using this SACH foot. So again, the question is that I want you to think about now is patients walked better, walked faster, and with less energy use using a prosthetic foot that could plantar flex compared to a SACH foot, which was surprising for a lot of people because we always thought that the SACH foot was best for these debilitated and older types of patients. So what is the foot that is permitting plantar flexion doing better than a SACH foot is doing? Okay, and in fact, I think I have an example of this type of foot. I know I was, here we are. Okay, so can you see this? This foot here is a foot that allows for plantar flexion. It would have a glove over it that kind of looks sort of foot-like, and it would have, I'm going to talk more about this later, but these flexible rubber bumpers in between here. So here's a plantar flexion bumper and then two dorsiflexion bumpers, but it allows for plantar flexion upon initial contact. Okay, so what does that do better than a SACH foot does? Go ahead, think about this for a minute and then chat me. Okay, good, some people are chatting. Okay, let's have a couple more people, at least a few more people, think about this and try and answer before we go to the next thing, okay? Okay, so actually, so far the best answer that I've seen is come from Esmeralda. Where's Esmeralda? Let me see. Esmeralda, wherever you are, virtual knuckle bump. Okay, so what this does better is shock absorption, because what plantar flexion does for us and other people with healthy sound feet is it's a shock absorption mechanism. And the actual plantar flexion of the prosthetic foot, it turns out, is a better shock absorption mechanism than is just the compressing of the soft heel of the SACH foot. So what happens then is that because you've got a higher external plantar flexion moment, let me find my skeletal leg. And I'm going to stop the screen share for just a second. Okay, because you've got a higher external plantar flexion moment, so this isn't dorsiflexing very much, it brings the tibia, which is actually the prosthetic pylon. We'll talk about that. The prosthetic pylon is an artificial tibia. It brings the tibia forward more and causes more of an external dorsiflexion moment. However, if the prosthetic foot can plantar flex, then it absorbs that external plantar flexion moment. Okay, and then also the SACH foot, which was very much better than what was there before, in addition to not absorbing the external plantar flexion moment really well, is not very good at accommodating the transverse plane moments that are generated proximally. Okay, so here is, I don't have an example of this, but in a couple of weeks, maybe you saw this or noticed this on the syllabus, our friend from Ozark B&O, Brandon Sutton, is going to bring in these boots, like cam walkers, that have prosthetic feet on the bottom. And these are the type of prosthetic feet that you guys are going to try walking in. Is kind of a fun activity and also a really illuminating activity. But what this does is it has this this flexible keel, which is a hard rubber, but it is flexible. So it allows for some accommodation of frontal plane forces, but even more important, it allows for accommodation of transverse plane forces. However, a couple problems. It doesn't have energy return, so we're going to talk about energy return in a little bit. and it doesn't accommodate to the change in stiffness with the needs of velocity. So Kayla and Mariella and Katie, do you remember working with Anna? So I'm going to see if I can see. I want to see your faces if you're there. So Kayla, there's Kayla. Okay, good.
Dr. Hackney, we couldn't figure out the camera in the classroom, so but I'm here.
Oh, okay. Who is that?
Mariella.
Oh, okay. Yeah, I see Kayla and Katie. Anyway, so do you remember as she got stronger and she got better with walking, that what we would see is that as she would go into terminal stance, she would have an exaggerated, maybe you don't remember this, but I do, she would have an exaggerated dorsiflexion angle on the prosthetic side. And that is because as she was walking faster, she's generating more external dorsiflexion torque. And this type of keel doesn't accommodate to people going faster. And so that's what this means, doesn't accommodate to the change in stiffness that we need with increased velocity. There are some mechanisms to do that though, so we're going to talk about that over the next hour or so. All right, so the next thing that we're going to talk about are called the dynamic response feet. So if you've seen Paralympians, for instance, who are using prostheses, they're using prosthetic legs that kind of look like this. And this is an example of the dynamic response. And these are just really torsional springs. We're going to talk about this more over the course of the next several minutes. Okay, so remember, I have some, here we go. Here's a good example of this. Here we go. Okay, so this looks a little bit like a blade. I'm going to show you a little bit more closely, right? But what it really is a torsional spring. So this is not, this is one for walking, not one for running, although I think that somebody could do some running in it, but it's not especially made for running. But what happens, and this is very strong, so I'm not going to be able to bend it very much, but what happens with heel contact is that the heel part of this blade will bend and then spring back. And then what happens actually, and this is even more important, with terminal stance, is that the toe part of this blade will bend into dorsiflexion and then spring back. And the more bend you have, the more potential energy return you get. So it's like a biological system. This is how our feet and ankles work also. And so what we need to have, and this is really interesting, what we need to have if we want energy return and we don't have much space is we need to have strategies to have more spring in a small space. So for example, look again at the keel of this prosthetic foot. What they've done in order to lengthen the spring is that they've bent it over like a horseshoe. Okay, so instead of just having it coming straight up, it's bent over, so the spring is longer, and the longer the spring, the more the opportunity for deformation of the spring, or bending of the spring, and the more the opportunity for energy return, right? Okay, so here is one of the first examples of an energy return foot. This is a Seattle Lightfoot, it's called. And as you see in the picture, it actually looks pretty natural. And so what this has got is a hard plastic spring going through the keel. And that will bend and store some energy. And then at terminal stance, it will return that energy. It's a rather short spring though. So this is not something that somebody could use for running, but at least in walking, it would give them some energy Okay, here's another variety, and this is it's got a lot of parts. It's kind of interesting, but it's got the interesting thing about this is that it's got two-stage resistance. So that two-stage resistance was made to make it seem more natural in gait. So it's got two plates, as you see here. It's got a inferior plate, and that inferior plate acts like the metatarsals, and that will bend in return. And then this superior plate is just doubled up, and so it's stronger, like your actual ankle joint is stronger than your MTPs. And when that doubles up, it also gives some energy return. So it was designed to, in that way at least, during terminal stance, provide a more natural gait. But it's very stiff, so it doesn't allow for medial lateral torque accommodation. Okay, here is the type of feet that you actually see with athletes, at least while they're doing this. Now, there's a thumbs up gesture. So there's a button that you can use that gives a thumbs up gesture. So you can just do that, or and that would actually be best. Give me a thumbs up gesture from the button if you remember a fellow named Oscar Pistorius. Okay, I'm going to see who remembers Oscar. So Justin does, I see so far. And Brendan and Jake and Nolan. Okay, and I guess that's everybody. Okay, so Oscar Pistorius was born with a particular birth defect that we'll actually talk about a little bit later this semester. But he was born with this birth defect bilaterally. And so in order to walk and live normally, really the best strategy was bilateral transtibial amputation. And he was such a good sprinter that he actually qualified for not just the Paralympics. He, forgive me, he qualified for the regular Olympics, and he actually qualified twice. The first time he qualified, there was some objection under the idea that maybe his prosthetic legs gave him an advantage over people with sound legs and feet, which is actually preposterous for reasons that I'll describe if you're really interested in. But then after being disqualified the first time, they took those questions to biomechanists and other experts and say, no, they're really cool, but they're not as good for running and sprinting as sound limbs and feet. So he actually competed with legs that are kind of like this in an actual Olympics. Brant, who you'll meet in a couple weeks, likes to tell the story that when he was being interviewed, he couldn't stay still, just because you see that these legs kind of more look like, I don't know, I think they look like a goat's hooves, or maybe a horse or something. They look like hooves anyway. They don't have very much of a weight-bearing surface. So they're great for running. They have a lot of potential for bending and energy return, but they're really bad for standing. If you're just trying to stand, they've got no heel, so you'll bend backwards. So Brant likes to tell the story that if you ever seen him interviewed, that he has to bounce around, he can't stay still. Unfortunately, Oscar Pistorius was then convicted for the murder of his girlfriend, and so took a really cool story and made it into a tragedy. Seems to happen a lot. There's things that we talked about. Disadvantages, though, doesn't accommodate medial lateral motion. And as is the case, I'll go back and show you these guys. So these are very, very stiff. And because the torques are really high when somebody's doing something like sprinting, then they will bend and release the energy, so they're very good for sprinting. But if you're just standing or walking, they're really too stiff for that. Okay, so here are some of the variations. you notice that this here is the pylon. And let me show you something. Okay, I'm going to stop the screen share for just a second so you can look more carefully. Okay, and again, please go to the speaker view so you can see this full size. But this is a fairly recent prosthesis. This has got a lot of new componentry. Take that tape off so you can see stuff better. And the thing between the socket and the prosthetic foot is the pylon. And this is actually a rather long, this is a socket that accommodates a rather long residual limb. Most of the residual limbs are shorter than this. So the pylon is also rather short. But the pylon, really, you can think of it as being an artificial tibia. And indeed, let me see if I can find another example. Here, this is a little bit more the normal shape, so it has the normal length of the pylon. And so you see the pylon is actually about the size and diameter of a tibia. So you think of this as the artificial tibia. Now, when you look, I'm going to screen share again. Okay, when you look at this, and I have kind of an example of this. This does not at all look like a tibia. This is a long strip, and it's a long strip of usually very stiff carbon fiber, sometimes metal, but lately it's more carbon fiber, so it's light, and it just extends the spring. Remember, the longer the spring, the more the potential for deformation. The more the potential for deformation, the greater the potential for energy return. And there's a bunch of variations, which I'll show you pretty briefly. Okay, so this is for walking. Here, this allows some bending and energy return, but the spring is not all that long. So it's good for for people who are walking, perhaps walking at a variety of velocities. This would be like a K3. And I want you to start thinking about, what sort of K levels these would be appropriate for. Now, remember we talked about the Symes amputation. The Symes amputation is done very frequently anymore, but it still is some. So what they did in order to provide some energy return is stack these plates on top of each other. Because with the Symes amputation, remember a Symes amputation is an ankle disarticulation, so you really don't have any space for a pylon, just an interface from the socket, then an artificial foot. But if you want some energy return, you have to have an imaginative solution. So their solution was stacking a bunch of plates together, such as you see in this photo. Now, give me a thumbs up or a show of hands. I'm going to look. And I think I asked this question before, but I don't remember the answer. Please tell me if you sprinted in high school or maybe in college on the track team. Show of hands, and I'm going to look. Okay, so Cameron did. Good. And Justin? Okay, so just Cameron and Justin, anybody else? Okay, Cameron, are you with me? Can you unmute? I have a question for you.
I am.
Okay, great. How are you doing?
Good. How are you doing?
Great, good. So you had shoes like this, right?
Yes, that is correct.
Okay, and as you see, for people who had experienced these, they have really no heel. Because what you want to do with sprinting is really, it's a 4-foot strike.
Yep.
And the reason it's a 4-foot strike is then you can really benefit from all the bending and then energy return of these biological springs in your foot and ankle. So the The midfoot spring is bending and energy return. The ankle spring has got a lot of bending and energy return. And that's the same reason that if you look at this prosthesis, that the heel doesn't touch the ground. So the heel doesn't touch the ground with the prosthesis, it touch the ground with this sprinting foot, because you want to really maximize the bending, because maximizing the bending maximizes also the energy return. Okay, so in the next few minutes, we're going to start talking about some of the jointed or articulated foot assemblies. And the most common is the single axis foot. So we've been talking about this before when we were thinking about the SACH foot. But the main thing that this does for us, like Esmeralda had pointed out, virtual knuckle bump for Esmeralda again, is that it allows a heel rocker and allows the prosthetic foot to plantar flex, and therefore it is absorbing some of that external plantar flexion moment. By absorbing some of the external plantar flexion moment, it keeps that moment from translating up the chain and causing knee flexion. So let me show you again what that means. And again, I'm going to unshare for just a minute so we can see this. Okay, so if the ankle is stiff, then you contact with the heel, it brings the tibia right forward. But if the ankle can move, then the foot can plantar flex. And if it plantar flexes all the way, and this is something actually that we want to happen for people with transfemoral amputation, because they don't have, a lot of times they don't have something in the knee that will keep them from falling down. People with transtibial amputation, it plantar flexes some, and so they have less external knee flexion moment. But one of the things, going back to the biomechanics that we had talked about in your first year here, is that the external plantar flexion moment, or any external moment, there's a couple things that can happen. It can be absorbed by the actual motion of the joint, or it can travel up the chain. The more it's absorbed, the less it travels up the chain. Really important idea. Okay, so here is an example of a single axis foot. So again, to emphasize and illustrate what we were talking about before. Okay, there's the ground reaction force coming from the heel, and there's the external plantar flexion moment. So here is an example of a single axis foot. So this here, this ball is actually just an interface with the socket. So there'd be a bolt that would go here, and then probably a collar that would go around, so you have a nice solid connection between the foot and the pylon here. And then here is the axis. Can you give me a thumbs up or something if you can see the cursor? That's really important. Okay, good. Okay, so here, let me get the cursor going again. Here is the axis, so it plantar and dorsiflexes around here. And here is the dorsiflexion bumper. Here is the plantar flexion bumper. And probably they're different colors because they're different densities that you want a greater resistance. In fact, you get onto a greater external resistance to dorsiflexion than you do to plantar flexion, because if you think about the biological system, what muscles are stronger, the dorsiflexors or the plantar flexors? Chat me. Dorsiflexors or plantar flexors are stronger? Okay, there we go. Okay, yeah, you're all right. The plantar flexors are stronger. So you need, and the reason for that is because you need more of an external, or you need more control of the external dorsiflexion moment than you do the external plantar flexion moment. So these individuals don't have muscles that are controlling the ankle joint. We need some sort of mechanical device to control those external forces on the ankle joint instead. There we go. Okay, so some of the other things. So if you have a single axis foot, like we were just showing, you, on the one hand, you have the absorption of those sagittal plane forces, and that's really helpful, but you don't have any absorptions of transverse or frontal plane forces. And those rubber bumpers, which we were talking about before, can wear out, and as they wear out, the resistance can vary. So a prosthetic foot might be great when it's new, but then become too soft as it gets older. Okay, now this is actually what I was showing you. This is an example of a multi-axis foot. This can allow a little bit more or absorb more torque in the transverse plane and in the frontal plane. So this has, I'll show you with my cursor here, what's called a split toe, but it's way more than, it's not toe as in your digits like we all have at the end of our feet. This is toe as in just the forefoot. But these allow for some accommodation of medial lateral forces. Okay, now a microprocessor foot. So you probably have heard of microprocessor knees. And microprocessor knees have become really important over the past several years in the construction of prosthetics and prostheses. You see fewer microprocessor feet, but what microprocessor feet can do is adjust the plantar and dorsiflexion angle in response to the angle of the surface. So for instance, if you are walking up a ramp or an incline, the ankle will adjust so it's more dorsiflexed. If you're walking down an incline, the ankle, the mechanical ankle will adjust so it is more plantar flexed. Hydraulic feet don't have any motors, don't have any sensors, but what they do have is a hydraulic cylinder, which, and the good thing about the hydraulic cylinder, and I don't have a foot like this, but I think, yeah, I've got a knee with a hydraulic cylinder, and hopefully I can kind of get the idea across by using this knee. So make sure, again, you're on the speaker view, so this is big enough. So again, hydraulic knee, and here it's flexing and extending. And the thing about these hydraulic systems is that the faster you move them, the stiffer they get. So what this does, and this does for the knee, and what it does also for the ankle, is it allows for change in joint stiffness in response to the higher torques that come from the velocity of, or a greater walking velocity. Okay, let's see, we're about ready for a break, I believe. Let me look at what is next here. Tell you what, we're almost finished kind of with this theme, so let's take just a couple more minutes to finish talking about bionic, or talking about prosthetic feet, and then we'll break for fluid balancing, as Dr. Cook would say. Okay, let's see. Go back to the screen share. Okay, now when I was in junior high school, actually, which was before any of you were born, there was, slide, there we are. There was a TV show called The $6 Million Man. And a couple years after that, kind of a spinoff came on called The Bionic Woman. Show me a thumbs up or something if you have seen or heard either of those television shows. They were in the 70s and maybe made it into the very beginning of the 80s. So I think before any of you were born. Okay, but so far I see only Jake had heard of either of those. But how about the expression bionic? Give me a thumbs up if you've heard the expression bionic. Okay, so a few more of you have heard that expression bionic. What bionic means is that it actually moves under power. So there's motors and batteries that will actually move it. And bionic upper extremities have been around for a couple of generations. But the bionic lower extremity components are much more recent. So we're going to talk about the bionic knee next time, but we're going to talk about the bionic ankle over the next couple minutes. So the bionic ankle has a plantar flexion motor that's able to generate torques similar to the plantar flexors. It is heavier than a torsional spring system like this. So but it is about as heavy as your biological foot and ankle. And what the research with small samples has shown that even though it's heavier, it actually improves the walking velocity and decreases the energy usage because of the extent to which the bionic ankle is actually generating some internal plantar flexion torque. Okay, and as you see, it actually increased the preferred walking speed very significantly. Okay, so this is a illustration showing how this system works. So this is just for your interest, and if you're really interested in this, you can look at it more. There's not going to be any test questions about how the bionic ankle system works. Okay, so when we come back at, let's see, it is right now 1:54. So when we come back at 2 o'clock, we'll finish talking about what is upstream, the pylon, the socket, and the suspension. Okay, go ahead and take 6 minutes for a fluid balancing break if you want, and I'll see you in a little bit. Okay, we'll give folks another minute. Okay, so let's start back up where we had stopped off, thinking about the pylons, shanks, and sockets. And I think we're going to talk about the suspension as well, and a little bit of the importance of alignment over the next hour. Okay, so we'll go back here. And there's a prosthetist, and he is doing alignment, and we'll talk about that. So alignment is mainly the orientation and position of the pylon relative to the socket, and the socket relative to the, or excuse me, and the foot relative to the pylon. Okay, so usually what you see are endoskeletal designs. So endoskeletal means that it has an internal structure, kind of like we have an internal structure. We've got skeletons. Exoskeletal, and you do see some things like this. As a matter of fact, I have something cool to show you, and I'll show this to you again. Okay, this here is a very old prosthesis. This predates the Second World War, so it's at least 80 years old, and has an endoskeletal shank of solid aluminum. But usually you see the endoskeletal design, and the endoskeletal design has a pylon. Okay, so show of hands or a thumbs up or some sort of indication, who among you likes cars? Not just owning cars and driving cars, but actually working on cars. We'll look here a little bit. Car person, anybody? No car people? Oh, Jake. Okay, good. Jake, can you hear me? Unmute so I can hear you, please.
Yep.
Okay, great. This actually looks like a part of a car. What does this look like to you? And actually,
Shock.
part of a car.
Shock.
Well, the shock, actually, we haven't had exactly shocks for, I think, since the 70s. Since the 80s, whoops, somebody has an idea. Let me look. Leaf spring? Okay, well, I suppose that's true. But let me describe this a little bit. So what we have had in cars since the 80s are struts, right? And what struts are is a combination of two things. So here is a shock absorber. And the idea behind a shock absorber, the objective behind a shock absorber is as a force damper, right? It absorbs the force. But here is a spring. So this is both a damper and a spring. So this actually behaves like a strut in a car, right? And struts have both shock absorbers and springs of some sorts. This is just a torsional spring. Actually, what you usually have in the struts of cars is an actual coil. But the objective is the same, that it has two functions, shock absorption and or energy absorption, and then energy storage and return. Let's see here, one more chat. Oh, okay. Shamek says SUVs and trucks still use shocks. Okay, I stand corrected. Okay, so remember that we were saying that one of the reasons that a transtibial amputation is usually more effective than something like even a transmetatarsal amputation, although you have, with a transmetatarsal amputation, you have a biological ankle, or certainly has a better outcome so far as function than a Symes amputation, or a really long transtibial amputation, is that you have space for a pylon. And some really important things can be built into a pylon. So I'll talk about that a little bit. So you can have a shock absorber, energy storage and return, like we were just demonstrating. And what you see here is a transverse plane torque damper. So this actually has a electronic system for transverse plane torque dampening and shock absorbing. But I'll show you actually something more. I'm going to stop my share for just a minute. There you go, so you can see this. Now, next time we meet, actually in person, so I think that will be when Brant comes, and that will be on the 14th. So a week from next Monday, you'll meet Brant, and we'll do some fun things together, and you'll see some cool stuff. That, by the way, I'm going to mention it again, but I'm going to say it now so people can start remembering, will be in the clinic. So on the 14th, we're meeting in the clinic. So plan on about 2 hours from 1 o'clock to about 3 o'clock. But anyway, this critter right here, this device, is a transverse plane torque damper. So if you were to actually step on this prosthetic foot and turn the socket up here with your hands, you'd be able to get some movement in the transverse plane. It's pretty stiff, but remember actually the torques that your lower body is generating with walking is actually quite high. So the stiffness that we have is appropriate. So that's a transverse plane torque damper that's built into the pylon. Okay. And now we're going to talk about sockets for patients with transtibial amputation. And there's a couple ways that these are done. They either have a socket without a liner or a socket with a liner. This here is probably an example of a socket with no liner, because the socket is very small, and this doesn't look like it would accommodate anything more than just the residual limb itself. So a liner is something like this. And so this would go actually over the residual limb, and you can see that this has been customized in a lot of ways with augmentations, a little bit of extra material here and here, and actually here. So those are all really pressure tolerant areas in order to, what's the word I'm looking for? In order to preferentially load certain areas. So this is a socket liner. And the reason that sometimes we use socket liners is just to increase the padding. So especially with patients who are vulnerable to skin and tissue breakdown, probably we want to use socket liners. Okay, now here's the shape of the socket, and the socket is not that advanced, but there's something really, really important, what's really, really important is the shape. So there's lots of effort that goes into making the shape of the socket. And I think we've talked about this before, but the shape of the residual limb is not the same as the shape of the socket. And the reason for that is that there are areas of the residual limb that are especially pressure tolerant, and areas that are especially pressure intolerant. Now, I just noticed, and I've been using this illustration for, this is the 14th year, and I just noticed a typo here. This should not be a relief area for the femoral head. This should be a relief area for the fibular head, right? Okay, so the fibular head goes here. And the reason it's important, first of all, it's a bony process, or it's a very prominent bone and very superficial bone. So it's vulnerable to pressure for that reason, but what else lives right at the fibular head? The common fibular nerve, right? So we want not to have pressure at the fibular head. the patellar bar, and we actually talked about the patellar bar before because we talked about patellar weight-bearing orthoses, but in transtibial amputation, and there's a few exceptions, but generally the patellar bar is really important because the patellar tendon, if the knee is flexed a little bit and weight-bearing and the quadriceps is active, the patellar tendon is a great weight-bearing structure. It's flexible, but it's very strong. So there's this indentation that goes very strongly into the patella. And now here's one thing that you perhaps would not have thought about unless you were kind of had learned more about this environment, that one place that we load up also is called the medial tibial flare. So if you, here we are. So on a tibia, this area here, not this here in prostheses, I don't know if anywhere else, but in the world of prosthetics and orthotics, this is called the tibial blade because it's so sharp. But just medial to that, there's a broad flat surface, which is actually a very good weight-bearing surface that is preferentially loaded up in the medial superior tibia. It's called the medial tibial flare. And we have not only, of course, the sagittal plane loading, but we have some frontal plane loading that is really, really important to how prostheses work. It's different between the transfemoral and the transtibial prostheses, but it's a really important thing, and so we're going to talk about it a bit. Okay, here are some socket liners, and some socket liners are also suspension systems. Okay, so we were talking just a minute ago about the frontal plane loading, and what we want in frontal plane loading is in what's called an abducted socket. Now this is something that you have to think about pretty carefully. I'll show you with these illustrations, and I'm going to show you with more of just some live stuff what that means. But here you can see, if you look carefully, the outline of the residual limb with this individual, and then you see the pylon, and she actually has a bit of a, I think, an endoskeletal pylon. She's got a combination of an endoskeletal and exoskeletal, but it's very thin here, so you can see this coming down. And so the reason that this is called an abducted socket is that the socket with the residual limb in it is abducted relative to the pylon. You could have called this an adducted pylon, and you'd be just as correct. However, that's not the language that we use. So if you're going to be in this environment where you talk about the frontal plane alignment of the pylon relative to the socket, and remember, whatever the socket is doing, the residual limb is also doing, we call it an abducted socket, again, because of the arrangement of the socket with the residual limb in it relative to the pylon. So the pylon is adducted, you see. That means that the socket is abducted. This is the opposite. So this is what we actually want for a couple reasons. One of it is that it loads up pressure tolerant areas like the medial tibial flare, but also because it gets the foot medially underneath the center of mass. And that's even more important because that allows for a more normal gait, as opposed to something like you see here. And these are some videos, you're going to see these in a couple weeks. These are stills that are taken from some videos, and what the prosthetists and the scientists did in some of these cases is make prostheses badly on purpose so that you could see what happens with this sort of problem. So this is called an adducted socket. You could also call it an abducted pylon, but nobody ever says that. People just say abducted socket. And so what that does, instead of causing a varus torque in the frontal plane on the residual limb, it's causing a valgus torque going in, forgive me, the opposite direction. And so the problem with the weight bearing is that's preferentially loading up the superior lateral shank and what lives there, the fibular head, with the common fibular nerve on top of it. So that's a really bad weight bearing area. But what's important for gait is that instead of bringing the base of support, which is the prosthetic foot, underneath the center of mass, it's taking that prosthetic foot farther away from the center of mass. Okay, now here's a drawing that is showing the pressure tolerant areas. And this is one of the things that we're going to do in a couple weeks. So I think I demonstrated this. This is very heavy. So we're going to have a bunch of these, and please don't wallop me or any of your classmates with it because it's very heavy. But this is a plaster positive mold of a residual limb that's been modified. So one of the things that we're going to do, and you should start thinking about this, is what areas are pressure tolerant, what areas are pressure intolerant. We're actually going to give you some pencils and have you draw in different patterns for pressure tolerant and pressure intolerant areas. But what this drawing here is showing you are the pressure tolerant areas. So in this cross hatching are pressure tolerant, and the areas that are just outlined are pressure intolerant. So of course this anterior tibial blade, they call it, the very sharp front of the tibia, is pressure intolerant, and especially here, the anterior distal tip, because remember, and we're going to talk about this a lot because it's really important in patients with transtibial amputation, they do not have a foot that goes to the ground. So instead, what they have to control the external knee flexion moment is just the tibia against the anterior wall of the socket. And what is most distal, so where is there the highest pressure, is down here, this anterior distal end of the tibia. Also the end of the fibula, then the fibular head are all especially, excuse me, pressure intolerant areas. Okay, so traditionally there was a plug fit, and I'm actually going, well, let's see, I'll show these to you after we just describe them a little bit. And then what was developed after this Second World War, based upon research that was done to help design, improve the designs of prostheses for people with amputation, was a patellar tendon bearing. So again, that became popular in the latter half of the 40s, and there's a few types of those. And all current socket designs are total surface bearing. So really the main weight bearing are these areas that we were talking about before, and most actual force is going through patellar tendon, but we want total contact through the whole residual limb because that helps prevent edema and helps maintain the shape, and also helps distribute the forces a little bit. So I'm going to unshare for a minute and show you something cool. Okay, so if you look at the inside of this very cool historic specimen of this rather ancient prosthesis, this is called a plug fit. And it's so called because it doesn't have the reliefs and augmentations to accommodate the pressure tolerant and intolerant areas of a residual limb after amputation that that modern prosthetic sockets do. It was just more or less shaped like the shape of the residual limb. So this is just leather inside with a hole where the end of the tibia would have been. I can use this, I think, to show you where the patellar bar is. So again, the socket would be usually made of some thermosetting plastics as a very, very strong material. And the patellar bar, just this indentation here, in order to really transfer that load to the patellar tendon, and especially the patellar tendon is taught because there is some quadriceps activity. So we'll talk about this in a tad as well. I'm going to share again. Okay, and this diagram here is showing why we have total contact, but at the same time why we have certain relief areas. Okay, and remember, there's something that I want to point out about this bullet point here is that we talked about, while we were talking about orthoses, that in order to have control of the limb, you need to have control of the bones. In this case, what you're trying to do is control a prosthesis. Well, you control prosthesis with the bones. So in the same way, we need to have bony capture with the prosthetic socket. If we don't, then we have poor control of the prosthesis. Okay, these are some variations of the prosthetic socket. In this corner here is the, and next door to it is the most common type. In fact, this has got a rather low profile. This has got a higher profile. This is called the supracondylar because the medial and lateral trim lines, we talked about that before, of the brim go above the medial and lateral epicondyles of the femur. So this is a low profile patellar tendon bearing socket. This is a supracondylar socket, same as this here, and there you can see in this drawing that the trim lines go above the condyles. And this is a supracondylar suprapatellar. That's what the SP stands for here. SC, supracondylar, SP, suprapatellar. And we'll talk about over the next little bit why we might use a suprapatellar type of socket. Okay, so when I was a new physical therapist, the most common type of suspension was a supracondylar cuff. Which you see here, and this is a leather strap that goes over the condyles and over the knee, and then down to the medial and lateral brim of the socket. That's no longer very common. This one over on the right is a thigh lacer, and that's quite uncommon. But before the Second World War, and probably during the Second World War, it was the most common type of suspension for transtibial amputation. So here is the thigh lacer. It might be used still under certain circumstances, and we'll talk about that over the next couple of weeks. There's an example of a prosthesis with the thigh lacer. Inverted T-strap is a possibility. I've never ever seen it with an actual patient, but this is suspending with a belt. And here is a supracondylar suspension with a wedge. So what this has done is it's actually suspended by the condyles. Okay, now here is something that you may see under certain circumstances. Especially if the transtibial residual limb is very short, what can happen is that that knee can hyperextend because there's fairly little that is holding on to the very short tibia. So what a prosthetist will do a bunch of the time, and what we as a community will do of people who are taking care of these people, is do the suprapatellar socket design. So what the suprapatellar socket design does is it helps to prevent hyperextension, especially with people with very short residual limbs, because here you have a force, and this is not going actually into the popliteal fossa, but a little bit below the popliteal fossa. So remember, we were talking about 3-point control. So this is a control system that helps prevent hyperextension. So here, a little below the popliteal fossa, and then the counterforce is above, superior to the patella, and inferior on the tibia. So that's the application for the suprapatellar socket design. Okay, here is a picture of a sleeve suspension, and how that works is that a person will put on the socks, and I actually have something more to show you here. I couldn't find this the other day, but then I did. This is an example of what is called a stump sock still. If you could actually feel this, this is rather thick. So this is like maybe, I don't know, probably because the technology of skiing and ice skating has improved, probably the socks are very warm, but not quite this thick. But when I was young, the winter socks could be really thick like this, but this is probably like a 6-ply, it's called. So the main reason for this is the thickness itself, because it helps take up space in the socket, because the space that you need is going to vary depending upon several things. You know, probably the time of day and its changes in edema. And if you're a fairly new person with amputation, then the residual limb is going to shrink, and you're going to need more and more socks in order to maintain a snug fit. So anyway, the socks would be the first thing that the person would put on the residual limb. Then the prosthesis, then that sleeve. So this is a sleeve that has very sticky material on the inside. It goes over the prosthesis, then over the thigh of the individual, and then the person can put their pants down. And I actually have a hyperlink, and I'll see if it will show for you guys. Okay, good. But we're not going to watch the whole thing. We're just going to watch starting, I think, at about a little after 4 minutes. Okay, so while you guys are watching that, I need to go get something. I'll be back in a second.
Dr. Hackney, we can't see it.
Oh, yeah? Well, crazy.
I think if you share a different part of your screen.
Okay, let's give her a try. How about now?
Yes.
Okay, so we'll start back at about 4 minutes. And I'll maximize that, in fact. Whoop, that did not help. We'll just do it this way. Okay, I think that gets the idea across. Okay, can you see the slide again? Give me a yellow if you can, or a thumbs up or something. Okay, good. Okay, now, type of suspension that is much more current is the suction suspension. The suction suspension is it has been around with transfemoral for a long time, but is kind of new to the transtibial. So let me I'll have to close out a bunch of things in order to get to the hyperlink that we want. So forgive me just a second here. That's not what I want to do. Let's see, close this one. Shoot. Okay, well, we'll go ahead and try it. Okay, now this is a short one, so I don't want to take too much time. So I need to, there we are. Okay, this is good. Okay. So we have actually we have a bunch of these. And so this socket liner has these ribs on it, and it's the ribs that provide the suction between the residual limb and the socket. Okay, that's good. Okay, now this is the most common. I'll show you the slide and then I'll stop the share so I can actually demonstrate this, the pin and shuttle lock. So what happens here? Okay, please put your Zoom screens on speaker view so that I am big because I've got something important to show you. Okay, so I've put my hand and arm in this socket liner that has this pin. And so like the fellow that you were just looking at, they would make sure it was clean and adherent inside of it. They may put socks on the outside depending upon if they need something to augment the fit of this. But then there's this pin in here, and then there is a hole on the bottom of the socket. And then what the patient would do is just step into the prosthesis and put that pin into the hole, and it holds on very firmly. And this is very fast. This is a very efficient form of suspension. It's both very good and it's very good at getting on and off closely. So when the person is finished with their prosthesis, then they just push this button down and they can pull the liner out from the pin. Okay, now I think we have actually time to finish here. I don't want to rush this, but because this is really important, but I think we can do justice with this by 3 o'clock, talking about alignment. So the alignment, like the bullet point says, influences the magnitude and especially the direction of torques, and actually the direction of forces, which are resulting from the torques being applied to the residual limb. Okay, so as we were saying before, what we want is a bit of a varus torque applied to the residual limb by the prosthesis. And the way that we do that is through the alignment that applies, well, forgive me, the way we do that is through the alignment of the prosthesis. Okay, and here we have, just to show you, because again, it's a very important idea. So here's an individual standing with the prosthesis. Here's the ground reaction force, and it's going, as is the case with us with two sound limbs, it's going medially to the knee. Because the foot is over here, it's medial to the knee itself, as is the case with people with sound limbs. And therefore is causing a varus torque. And so loading on that, in the frontal plane, loading on that medial tibial flare, which is a very good weight-bearing structure, and also weight-bearing on the lateral shaft of the fibula. This is causing, or this is showing a collinear that is straight through the prosthetic limb, but that is not what you want. Actually, I thought I had erased or deleted this slide. Here it is, but I don't think you need to spend too much time thinking about what you do not want. This is what you do not want. You want actually a frontal plane torque in a varus direction. Okay, so the other things that you do is that you put the socket in some flexion. I have here a couple things to help illustrate that. But we'll talk about this drawing here. And I'll show this to you a couple ways because this is really important that you understand. But the socket is flexed. And because the socket is flexed, the residual limb within the socket is also flexed. Just to show you so you're really clear on what I'm describing, I'm going to unpause and show you with some devices here. I'm going to unshare and show you with some devices. Make sure that you're on the speaker view here. So here I have a prosthetic foot with a pylon. Here I have, this is actually a socket liner, but I think I can get the idea across very well. I'm going to get a little bit farther away so that you can still see. Okay, so by the socket is flexed, what we mean is that within the socket, the residual limb is flexed relative to the pylon. All right, and this is really important because we want for the patellar tendon to be tense. And for the patellar tendon to be tense, the quadriceps needs to be active. And what makes the quadriceps active is a more extended external knee flexion moment. So what's a good way to have an external knee flexion moment is to flex the socket like this to make sure that the quadriceps is working against that moment. Okay, and these are just some directions. So if somebody was using an Oxford shoe, which is rarely actually used these days, but if they were, this is called the breast of the heel that I'm pointing to right here. Or in an actual Oxford shoe, like I wear some of the time, this is the breast of the heel. So the epicondyles within the residual limb within the socket should be anterior to the rest of the heel, but actually I think more important, and because this is still true no matter what kind of shoes the individual is working, they're actually anterior, here we go, anterior to the pylon. Okay, and so what happens with walking, so far as the forces applied to the residual limb, are that we have an external flexion moment with initial contact, and so that has to be resisted with activity of the quadriceps. And then during mid stance, we have an external extension moment. And then during terminal stance, and this is true with us too, we have again an external flexion moment as the ground reaction force vector goes to the rear, show you with the cursor here, goes to the rear. Actually, let me do this. I'll draw that in. So it's going to the rear of the sagittal plane axis. I'll draw in a circle, the sagittal plane axis of the knee joint. Okay, so there's a couple things that a prosthetist could do with the alignment. And there's a couple of types of alignment, and Brent will talk about this in a week and a half when you meet him probably. There's what is called a bench alignment. So bench alignment is what is done before the patient ever gets the prosthesis, and then dynamic alignment. Dynamic alignment are little tweaks that a prosthetist might do in order to change the torques being applied to the residual limb by the prosthesis. So if we have the foot being longer, and it couldn't actually be the prosthetic foot that is too long, but in this case, what it's actually showing is that the pylon is too far forward. We have a really high external extension moment during, that is an external knee extension moment during mid and terminal stance, right? Because the ground reaction force is coming up from the forefoot for way longer and with a way longer moment arm than it is for the normal situation. Or if the foot is too short, they call it, and actually what this would really do is that the foot is too far posterior, then you have a high knee flexion moment during terminal stance. So it would, as we were describing, if the toe lever is short with those patients, then that would shorten the step length on the opposite side. Okay, so here is a chat question that I'd like you to think about for a couple minutes. If you were a prosthetist, and I don't know, there actually have been a couple of graduates of our program who are considering going back and doing that. So there would be both a PT and a prosthetist, so that would be like a wide variety of skills. And we know what kind of patients the therapist like that would be working with. But if you were a prosthetist, just so I can get you to think about this, and you had a patient who had just gotten their prosthesis for transtibular amputation, you saw that with stance phase and terminal stance, they were hyperextending. What could you do to the prosthetic foot or the pylon to help that problem of hyperextension? Okay, so, and that's a problem that I'd like you to think about for the next couple minutes. If you were a prosthetist and you saw a patient who had a problem of hyperextension during stance and terminal stance, what could you do? Think about these diagrams that you're looking at in order to answer that. Okay, so I'm looking forward to seeing some cool chats. Okay, hey, okay, so I'm looking at your answers, and 4 people answered, 4 or 5 people answered, and I must say that I love your answers, and that's absolutely right, and that's especially cool because that's something that you could do as a therapist. You wouldn't have to like ask anybody's permission or mess with the prosthesis, and you messing with the prosthesis, unless you're also a prosthetist, could probably get you in legal trouble. But what a bunch of your classmates said is that you could use a heel lift. A heel lift would cause an increased external knee flexion moment by causing an increased external knee or external plantar flexion moment, and therefore counteract that effect of hyperextension. The other thing that you could do if you were a prosthetist is move the foot or the pylon backwards. And this is actually very possible. Here, let me stop the share for a second because I want to show you something. Okay, so if you look closely at this interface, this coupling actually, where the pylon meets the socket, you see these Allen screws. And with these Allen screws, a prosthetist could adjust the pylon forward or backward a little bit. And then with these Allen screws on the medial and lateral side, a prosthetist could adjust the pylon inward or outward, or medially and laterally a little bit, depending upon what they see with the gait. And so if a patient had that problem of hyperextension, a heel lift is a great idea. And the other great idea, which is not really available to you, is to move the pylon backwards a little bit. And that will shorten the lever of the foot. Okay, we have, it is 10 minutes to 3. You know, we were officially meeting till 4, but I want not to do that because that really causes diminishing returns. Let me see though how much we actually have left. In this lecture, I think we're very close to finished. Okay, yeah, just one more slide. Can you stick in there with me? Okay, so final slide, and then we are done for this afternoon. Okay, so we were just talking about the what is called the anterior offset or the posterior offset. If we move the pylon or the foot forward, it's anterior offset, increase external extension moment on the knee. Move the foot or the pylon backward, it's called posterior offset, increase the external flexion moment on the knee. And what we have here in this diagram is inset and offset. So the inset is what you see on the right, and for a couple of reasons, that puts the foot more underneath where the center of mass is going to be in a person walking during the single limb stance, and also applies that varus moment upon the residual limb. And that varus moment is what we want because it more loads up the pressure tolerant areas. But an outset, and you may do this if you see too much inset, and we're going to again look at the videos in a week or two, and you'll see examples of both. You saw some video stills from this particular video that is showing too much AB or A deduction of the socket. But if we have too much outset, which should actually be an AB ducted socket, so the foot is lateral to the socket and the foot is lateral to the center of mass, two things happen. You either have to bend the trunk, and that's the most common thing, you know, kind of like a compensated Trendelenburg or gluteus medius gait, in order to keep the center of mass on top of the base of support. And that's actually what you're going to see in this video, or the step is really, really short. The second problem with this is that you're loading up the fibular head over on the lateral side of the residual limb, which is a very pressure intolerant area. Right? Okay. Unmute yourself and say right.
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 Okay, great.
Right.
All right, super. We're done for this afternoon with this. I'll hang around for a few minutes in case there's any questions. And then I'll post a video of this lecture when it's ready. Okay? Okay, did you see that I put a tab with the videos of the lectures if you want them? Okay, great. I guess not. Bye. Good to see your names.